Okay, so let's recap. What we did for now is that we saw about convex sets, about convex function, which is the definition of them, the definition of an epigraph, how to prove something is convex, set or function. We saw also like if two sets are convex, that their intersection is convex too. And we used also Asian gradient and Asian. We used also epigraph to demonstrate the convexity. But now I want, before diving in, taking you through three questions to make you understand like general theory of convex optimization. First, I want to tell you that in convex optimization, we are interested of problems of the form inf of f such that x is into s. Okay, so that's the main thing we're interested in here, where f is some convex function and s is some non-empty convex set. So that's about it. Um, yeah, the three questions I wanted to go with you is first, do you think the problem is bounded? So I'll let you answer by yes or not, and we go through the video. And so an advice can be like to take an example. Generally, when I ask you to take an example, it's because it's wrong. So in priori, it does not have to be bounded. Uh, so not a priori. Indeed, if you take like for example f of x equal x and s being r, so if you needed to write it in perfect form, you write it like this: nth of x such that x is into r. That's the standard how you'll see written as a comics program. And so with this, there is no lumbar bound on the objective value, and we refer to the problem as be unbounded, like so you have this, so you have your line going like this, and there is no bound, it go until minus infinity, so no, or plus infinity, so it's not bounded. Second question, which is less or more related to it, is if bounded, is the optimal value achievable? So if bounded, optimal value, I'll let you think about it. Once again, you can think to a counterexample. So indeed, we have a counterexample. If this time you take f of x, which will be equal to, so in other words, if the infimum over S gives some value R, does there exist an explicit X being into S such that f of X equal R? Now, for example, if you take once again f of X, but this time the problem being bounded, we change the convex, the non-empty convex sets. So such X is into 0, 1. And then the optimal value will be 0, but 0 is not into S. So it implies optimal value not achievable. Maybe you can draw it. So now let's say it goes from here to here. So you have 0 and 1. And so maybe the, don't know, like, oops. You do not reach the 0, so I think it will be a correct formulation about it. And third stuff, can we actually solve the problem? Like, if we find a convex formulation of the problem, can we solve the problem? And the answer is also not a priori, not always. Like, does there exist an algorithm that guarantees that to find an approximation to the optimal value in an efficient time would be wrong? Unfortunately, convexity does not apply efficiently solvable. One example comes from quantum separable states, which is like separable states is mm, like, take this. It's like you have A and B, two system. Then you can separate A from B. And if you cannot separate them, it will mean that say your B is not a separable state. So here is a counterexample. So you know the definition of separable state is just this sum of A of a probability of first system by second system. And so such, well, yeah, that's it. Uh, which, so as I said, like P being a probability, so Pi of I being into P, space of probability, this being like for A, so being into this space, and this being into the space of P. And so yeah, which is a convex subset of DAB. So this is I think it is a convex subset because like when you have this, for example, this, then you know when you have A and B, then this is a subset because here like they are separable, so they're like this, but here you know you have this stuff in more, and so maybe that's about it. But anyway, it's a convex subset. But when you test this there separately, like this is NP hard to for artistic membership, you know. And NPR, like it's complexity classes for algorithms. Yeah, you have P and NP is for quantum. Well, like for difficult problems, you have also problems not quantum that are not that are NP, but well, in complexity theory, you most of the time like try to understand most of the time NP in comparison of P, where P are polynomially solvable problems and NP are not polynomially solvable problem, and so you have also I think NP easy, NP medium, and NP hard, and so NP hard is even harder than NP normal. So yeah, it's really hard to compute, and so computing something about it is really hard. It's a tough. So as NP hard said, it's hard then to compute something about it. Even so, it's a convex optimization problem. So we will not really care about all of this in the set of the in the following of the course, but just wanting to let you know about these three questions. You know, it's interesting to know about it.